A child pulls a wagon at a constant velocity along a level sidewalk. The child does this by applying a 25 Newton force to the wagon's handle, which is inclined at 25 degrees to the sidewalk below. What is the magnitude of the force of friction in the wagon? So let's do a real quick drawing. Here, I'm just going to draw the world's laziest wagon, which is a box, and I'm going to put it on a surface. Awesome. So let's draw our forces. Well, we know on this wagon, we should know by now that there's a force that pulls down. And I'm going to draw my force that pulls up in a second too. Now, these will be a little bit interesting compared to what we've had before. And this one is our, I don't know why I keep making that, our force, normal force. And this is a force of gravity. Okay, so there's those two forces. We know these are going to cancel out. But we also say have a force that's pulling on this wagon. I'm going to draw it like this. You can draw it however you'd like. And this is an applied force. Force applied. Or let's actually just call it FA, because that's something we've routinely done in this class. And the thing to realize with FA is that if we draw, let me just draw it down here and move it on up. If I have this right here is the x-axis, and FA makes an angle in my example problem of 25 degrees with respect to the x-axis. And this is good for us because remember all of our angles have to be measured with respect to the x-axis. Or in this case it says the horizon or the sidewalk, something that goes along the x-axis. So this is fine. The other thing we have to realize, we have one last mysteriously annoying force, and I'll make it purple. And it's going to be this way, and it is going to be our force of friction. Okay, so we've got 4 forces acting on this thing. The thing to remember, guys, is this. I always like to divide my paper. I'm going to scroll down a little bit. That it's at equilibrium, so that means our F net equals 0. And the important thing to realize now is that F net x equals 0 and our F net y equals 0. And that can be newtons. You can add that on there. So we'll say F net y is the sum of all of our forces in the y, and F net x is the sum of all of our forces in the x. So, okay, let's do some real quick basic adding these things up. Oh, come on. So if I go down a little further, I have sum of f x equals f of f. Take a look. F of f, that's on the x-axis. And the sum of f y, well, that is f g, and we'll make it negative, and we're going to have a positive fn. And I'm putting opposite signs because they go in opposite directions. Okay, and we can make this negative if we really wanted to because it goes to the left. Okay. Now, the one thing to realize, guys, is this, that this particular FA, it can be broken into 2 components. A x component and a y component. So if we just want to, we can destroy this and have our fx and our fy. And I'm going to draw these here. I'm going to put them in red. So I'm going to have an f, we'll call it fay, that's really like that, plus fax. And so now we have all of our forces added up, and everything's on the x and y axis. Now remember, this one says, real quick, just to be specific, what is the magnitude of force of friction on the wagon? Okay. Now, what axis is the force of friction on? It's on the x-axis. So that means this is the only side we care about. We only care about the x side. The y side, guys, just ignore it. Ignore the y side and focus on the x side. So we have this. And once again, we know this is at equilibrium. So we know these equals 0. So we know this. F minus plus f a x equals equals 0, and therefore FAX equals FF. So if you can find your FAX, you can find your FF. Now, how do we find the x components? Well, Mr. Lee gave this to us, and I'm going to put it in my notation, not his. I said Fx equals, or sorry, let's go all the way. FAX, the force applied in the x direction, equals the force applied cosine theta. That's all you have to do, guys. It's that simple.